So we've seen what a one sample or one-way chi-square looks like. Let's add another variable to it. And a really good example, and I'm going to kind of summarize the numbers they come out with, but a really good example is on page 433 on again the Whit book. We're going to do an example here. I'm going to do this two different ways. I'm going to crank it out sort of halfway by hand, and then we're going to show you how that works on SPSS. If I can remember how to do that. I think I can. I can usually figure it out. Okay, this is the lost letter example. What happened, the setup is, and you can, again, this is spread out over several pages, is we take a couple hundred letters. We address them to ourselves. We put a stamp on them. We conveniently lose them in different neighborhoods. And we want to see if people are nice enough to pick them up and just put them in the mailbox. And we're going to compare neighborhoods. We're going to lose some letters in the downtown area. We're going to lose some letters in the suburbs. And we're going to lose some letters on the college campus. And we just want to see if there's any significant differences in terms of neighborhood by whether or not people are more likely from one neighborhood to return them, be nice enough just to pick them up and put them in the mailbox than any other neighborhood. So you've got a table on page 433. And let me just kind of, I'll put the numbers in. I'm going to kind of abbreviate this just a little bit. But so we've got neighborhood is one of our variables. That's one variable, but there's more than one variable here. This is a two-variable chi-square or two-way chi-square. So neighborhood is either downtown, the suburbs, or on campus. The other variable is whether letters were returned or not. So the other variable I'm going to put over here on the left side and just say returned, question mark, either yes or no. Now notice that both variables, the neighborhood and the yes/no, these are both nominal variables. All we can do is count, categorize, and tell how many of each one. Everything's nominal here. So, of the yeses, and I'm not gonna put everything down the table yet. I want to show you where some things come from first of all. For the yeses, for downtown, we had 39 yeses. So 39 letters I dropped downtown got returned. 21 did not get returned, which means we lost 60 letters downtown. In the suburbs, 30 were returned, 40 were not returned, which means we had 70 letters we lost in the suburbs. On campus, we had 51 returned, and 19 were not returned, which means we had a total of 70 that we lost on campus. And the example, from this example, a point I want to stress is that things don't have to be spread out evenly. You know, you can have more than one, kind of like those independent t-tests. You can have more in one category than another. It doesn't have to be even, thankfully. Now, if I look at my totals the other way, we had 120 letters returned, and we had 80 letters not returned. That means that accounts for 200 letters both ways. 60 plus 70 plus 70 is 200, and 120 plus 80 is 200. Now I'm really going to have to squeeze in some writing here. And I'm going to do that by, I'm not putting the chi-square formula here. You already know what that is. I said it wouldn't change. It doesn't. But how do we calculate expected value? Now, it gives it to us in the book, but where do the numbers come from? Well, if there were more overall yeses, if there were more overall yeses than nos, wouldn't you expect more overall yeses for each of the three categories? So we would expect the top numbers, all three of the top numbers, to be higher than all three of the bottom numbers. I see a problem right there. I don't know if it's a big enough problem to get excited about, though. And if downtown I drop 60 letters, we drop 70 in the suburbs, and we drop 70 in campus, wouldn't you expect the campus and all of the campus and suburb numbers to be larger than the downtown numbers? So here's how we fit that together. Again, you don't have to do this with SPSS, but here's where the expected values come from. The expected value, we call it F sub E, that is equal to, for any particular cell, and I've got 1, 2, 3, 4, 5, 6 cells, is whatever the column total is times the row total and I'm copying the formula on the top of page 434, so when you can't read my writing, that's where it's coming from. And we're going to divide that by the overall total. So let's calculate that for the expected number of yeses for downtown, where I drew the parentheses. The column total is 60. The row total is 120. And we're going to divide that by 200. And I think we're going to get, if I can do that in my head, without checking there, we get 36. Is that correct? So I didn't leave myself enough room here. Now, if I know that I have 36 downtown I expected to be returned, how many would I have expected not to be returned? Keep in mind, we dropped 60 downtown altogether. So if we expect 36 of those to be returned downtown, how many, the rest of those 60 we would expect not to be returned, which is going to be 24. So I don't need to invoke this formula again to get this 24. Agreed? If you know, let me point. If I know I expect 30, I've got 60 altogether downtown. I expect 36 to be returned. Well, 36 plus some number has to equal that 60. The sum number is the 24. So once I'm given that, it helps me get another one. Let's calculate another. Let's calculate the one for the, it can be any of these. I'll just pick the, let's pick the one in the suburbs. Let's pick the expected value for yes in the suburbs. Oops. You already got that figure? It's 42, did you say? Oh. Well, okay, let's do it by hand. The column total is 70. And I'm calculating where I drew the blank parenthesis for. The column total is 70 times the row total is 120 divided by the overall total of 200 is 42. Yep. So let me get rid of that. Well, let me finish some things out first. What else can we know if we know the expected number of yeses for the suburbs is 42? What else can we know? And you can go a couple different ways here. let's just keep with what we said before. In the suburbs, if I knew I dropped 70 there, and I expected 42 to be returned, that would lead me to think that 28 would not be returned. So my expected value for the suburbs no would be 28. Do I need to do this formula anymore? I do not. Because if I know I expect 120 to be returned, well, 36 plus 42 plus some number is 120, and that other number I believe is 42. And then the last thing, I can get this one of two ways. Either 24 plus 28's got to equal 80, or 42 plus something equals 70, and the other something is 28. So I had 6 cells, but how many times did I need to do this formula? Had to do it twice. I'm going to erase the formula because I don't need it anymore with this. But here's what I want to show you about this formula. Remember we had to look up degrees of freedom? Okay, if you look at the bottom of page 434, you will see that degrees of freedom for a 2-sample chi-square equals the number of rows, the number of columns minus 1 times the number of rows minus 1. How many columns do we have? 3 columns and 2 rows. 3 minus 1 is 2. 2 times 1 is 2 degrees of freedom. The 2 times we had to use the formula. There are 2 degrees of freedom. Once you filled in the 2 pieces, everything else fell into place. So 2 degrees of freedom. All right. How many times you have to use the formula? Or it tells us why SPSS is going to spit out 2 degrees of freedom when we make them do all the work in a minute. So in the interest of the space, and so you can read some of my writing, can I go ahead and go to the next slide or make a blank slide? And I'm going to pretend that when I did this formula, and I'll write it again, which it doesn't matter which does it say first. E, I think. Over. You don't ever you don't count the total as a column. It's where you have data. So when I invoked this formula, I had 6 different cells. Three neighborhoods and 2 categories for our returned or not returned. When I invoke this formula, I'm going to pretend I've done it. I'm going to get 14.02. There's my chi-square value. Without cranking out my hand, I'm just looking to see what the book cranked out. I got it by saying, if you look at this cell right here, 39 minus 36 is 3, 3 squared is 9, 9 divided by 36 is one of the 6 numbers that you have to add together. Okay, look at that. Watch me do this. No. To calculate the chi-square value, I have to do it for all 6 of them. I just did to get the expected values. I had to do it for just 2 of them because that's 2 degrees of freedom. The question was, how many cells do you use to calculate chi-square? And the answer is all of them, all 6. But we didn't need to do the expected value for all 6 cells because things fell into place. But to calculate chi-square, which we're not going to do, but it involves all 6 boxes. So once we do all 6 boxes, we got a 14.02. I think I'm looking at the right number. Now, if you go to the table, and again, we need the critical value only when we're not using SPSS. I'm about to show you how to use SPSS. But let me finish it out this way, so when we do SPSS, you'll see we're getting the same answers, and you'll see where they come from. That's why I'm making you watch me. I'm entertaining you. Okay, so we had 2 degrees of freedom. We are testing at the 0.05. I'm looking to see that, yeah. And my critical value is 5.99. That's 0.05 level of significance and 2 degrees of freedom. So I can compare, because my chi-square exceeds the critical value. In other words, 14.02 is greater than 5.99. The answer is there is a difference, a significant difference in the return rate depending on the neighborhood. Keep in mind especially the 14.02. No, the 14.02 came from all 6 pairs. I can be really mean and make you watch me crunch that out. Well, I'm gonna start. I'll start it. The chi-square value, not the degrees of freedom. It's just like your t-value and degrees of freedom are 2 different numbers. Your chi-square number and degrees of freedom are 2 different numbers. The chi-square number comes from 39 minus 36, whatever that squared is, divided by 36, plus 30 minus 42. No, you don't really. You just want me to stop, right? Yeah. And I'm just going to say ... say all 6 of those added together. And I'm not going to do it because, again, SPSS does it for us, but I want to show you that we're going to get the same meaning. Again, with SPSS, you don't need critical value. You don't need the table. Our point is to find out what the p-value is. All the table will tell us is it less than 0.05 or not. SPSS will tell us, oh, here's what it is more specifically, and you can tell if it's less than 0.05 or not. Okay. All right. Now, keep your finger on page 445. 445. The table that I reproduced when I figured out the expected values and all, the very bottom of it. And watch what I'm going to do with SPSS. Okay, I'll wait. Look at the table. Well, it's 19.14. The bottom of 0.4. It's the same problem we're working on right now. I'm just going to make SPSS do it. No, we're going to have to put the data in SPSS ourselves. Yeah, it's not a pre-existing data set. We've got to, and that's why I want to show you. Okay. When I go to variable view, we said we had 2 variables, right? One variable is the neighborhood. I'm sorry, that's the wrong. That's your homework problem. Go back. I'm sorry. No wonder you were mistaken. Go back to page. Yeah, I'm sorry. Page 433. I'm sorry. Yeah, the 445 is your homework problem. That's the Titanic problem. So you're going to do the same thing with that as I'm doing with this right now. Okay. So one variable is neighborhood. Right? And we've got 3 different neighborhoods. So what I'm going to do, and I'm going to go over to values, and this is where I'm going to tell it. I'm going to use 1, 2s, and 3s. I'm going to let 1 be downtown. Remember how I do this? I click on the value. I let a value of 1 represent downtown. Add that. A value of 2 is going to represent the suburbs. Add that. And a value of 3 is going to represent a campus. Add that. And that's okay. The other variable is whether it was returned or not. I'm just going to put returned. And again, I've got yeses and nos. I'm going to label it the same way. I'm going to let 1 be yes. And I'm going to let 2 be no. And again, this is recorded, so you can go back and rewind this a little bit if you need to watch me do this slower. So 2 is no. So I've done this before, but I know it's been a while, and we're doing this in the middle of everything else here. So 1 is yes, it was returned. 2 is no, letters were not returned. Now, what about the actual numbers? This will make sense. What about the actual numbers in the body of the table that we actually observed? Let's do something real radical and call that number. And I'm not going to do anything else with that. I'm just going to call it number, and we're going to put it. Because we're going to just put in numbers, and that represent actual quantitative numbers, not just labels like the one neighborhood does. Okay, so excuse me. I'm going to go to data view now, and these are going to become column headings. And I had in my neighborhood labeled number 1. And in the number I had returned, which is also number 1, how many did I have returned from the downtown neighborhood? What was the number for that? And again, we're just looking at observed values. Because neighborhood 1 means downtown, returned 1 means yes. So returned, yes, returned, and downtown. There were how many? Sounds like, start with, that's the answer. Yeah, 39 is, yes, nominated on the board and seconded in the classroom. So yes, there are 39. But I also had neighborhood number 1 and a number of letters that were not returned. So I'm going to give that a neighborhood 1 and a return 2, meaning no returned. And how many were not returned? 21. What about for neighborhood number 2? We had some that were returned, so a 2 neighborhood, a 1 returned. So how many were returned from neighborhood number 2? 30. And we also had neighborhood number 2, which was, again, the suburbs again. Some of those letters were not returned, so I'll give that a value of 2, meaning no. And there were 40 of those. Very good. And my neighborhood number 3, which was campus, some were returned. 1 means yes, returned. 51 of those were returned. And also in that same neighborhood number 3, not returned, so we'll code that at 2. The number not returned on campus was 19. And that's all our SPSS file looks like. You're laughing at me already. Okay, all right. First thing we're going to do is we're going to go to data. And we are going to weight cases. That means, the more numbers you have in a cell, well, let's see, what's a nice way, scholarly way? The more numbers you have in a cell, the more numbers you have in the cell. So we're going to weight cases according to number. Oops, sorry. Because the others are just labels. Number's a quantitative one. Question. I can even go further than that. It's always going to be number if you call it that. So I am going to weight cases. So my default is don't weight cases, but I'm going to say I'm going to weight cases. So I want to move number into that frequency variable because number is the frequency in that category. Matter of fact, it's the only one of these three variables that is a frequency. And I'm going to click OK with that. Oops. It's an old output I don't want. Make sure we still have that. I do. Okay. Okay, I don't want that output window. Again, every time you do something, it gives you an output when it says you did something. I'm going to go to, as you would guess it, Analyze. Close it. You don't need it. It just tells you, hey, you did something. Well, it didn't give you a result. It just told you did something. It just close the output window for now. Matter of fact, I think there's a way to set it where it doesn't do that all the dang time, and I've set it that way, but it keeps coming back on me, so I just gave up. Okay, go to Analyze and go to the first place we went to. We did go to Descriptive Statistics, and here's a word I told you we would use: crosstabs. Crosstabs in this context means you're doing a two-variable chi-square analysis. So we go to Crosstabs. And when I click Crosstabs, it's going to open up a window with some boxes. Now, what were my rows and columns? Anybody remember that? Let's just use the same ones. The neighborhood was our columns, and the number, whether it was returned or not, were our rows. So we're just labeling the rows and columns just like we had. Again, this is a little bit like the ANOVA and the independent t-test, where the way you put the data in SPSS doesn't always look like it does in the chart they give you. I'm going to go to Statistics and look at all the things I can come up with here. I'm going to select chi-square. And let's see, do I want anything else or not? I want that. I'm going to select phi and Kramer V because that's something we report in a write-up, which you don't have to do a chi-square write-up, but you'll see that in examples later. And do I want anything else or not? Yeah, I want to select cells. Actually, I think I need to continue first. Now I want to select cells. What have we not talked about in SPSS so far that we had when we did it by cranking it out the old-fashioned way? We didn't talk about expected values. I'm going to have that calculate the expected values for us. Under cells. If you click cells, it'll open up this box, and we want to click. It's going to give us observe because, of course, we want that. We put that in. I also would like to see the expected values. I'm going to click continue. Now, when I click OK, I'm going to get a pretty messy output window. I'm just going to tell you. But we don't need all of it. We just need a couple of key things. Ready? Next is OK. Okay, see, it's not too bad. Actually, okay. Let me tell you the key things to look at right here. The main, and I'm going to just point out a couple of them right now. The main key thing is under chi-square test, which would kind of make sense since we're doing a chi-square test, wouldn't it? And what else is going to make sense is one of the lines. Which line do you think is going to make the most sense in this table? The one you think. Yeah, the one that says chi-square. This one. Now, here's where they change language. I don't know why. Don't ask me. I could lie and make something up, but we don't have a column called SIG, significance, for our p-value. That's what this is. Asymptotic significance. I don't know why. Anyway, our p-value is 0.001. Oh, look at our degrees of freedom, by the way. It told us 2. And we remember how we got a 2 a little bit ago? It does it for us. You don't have to, and if you look, the question was, we don't have to divide anything by half. That p-value is always good. If you will look back in Green and Salkin on page, there's a little subheading on the bottom of page 430. It says chi-square is non-directional, so you don't have to worry about directional. So yay. So there is actually something you don't have to do. Again, the question was whether or not we ever need to divide that p-value by 2, and you don't. You don't ever. So again, this means that the kind of neighborhood we lose letters in, there seems to be a difference in terms of the likelihood if we're going to get them back or not. Now notice the table right above it. Look at these lines. Those are our expected values. So when you do it in SPSS, you kind of do it backwards. You don't have to feed in all the information. You put in some basic information. It spits all this stuff back at you. The idea is correct. If you put in your regular count, it will calculate the expected counts for you. Yes. So the bottom line right now, and again, follow-up analysis notwithstanding, I may talk about that in a few minutes with the next example. The follow-up status notwithstanding, the kind of neighborhood matters. Well, are you more likely in downtown than suburbs? Well, I don't know. That's the follow-up stuff, but I'm not going to worry about that in this example just yet. Questions, comments? Let's do another example. Open up the data. Open up lesson 41, data file 1. Lesson 41, data file 1. And the data is already entered for you here. Data file 1 looks like this. If you look at Green and Salkin on page 3, the lesson starts on page 366, but look at the scenario, the second scenario called homogeneity of proportions. Don't worry about why it's called that. It's just a better example. This is a better example to use what we were doing already. The second example that starts about a third of the way from the bottom on page 367. Claude, the bottom line, Claude wants to determine whether young men are unjustifiably more likely to treat elderly people in a condescending manner. So we divided women into 3 ages, and I'm looking on the description, page 369. Young, middle-aged, and elderly. I love the way they define this. Young is the 20-year-old, middle age is the 43-year-old, and the elderly is the 72 years old. I got to tell you, 72 sounds younger and younger every year I get closer to it. So we're going to have a bunch of men. We're going to measure how they treat these three women of different ages, how condescending they are. So either they're condescending or they're not condescending. Let me kind of draw that out for you in ways that we had this a little earlier. I'm going to say our ages are young. We'll call that a 1, middle-aged. Call that a 2, and elderly. Call that a 3. And they were either condescending or not. Either yes, which we'll call a 1, or no, which we'll call a 2. Now notice what I did. I kind of did this on purpose. I've got my yes, no's as the column. It doesn't matter. It doesn't matter what columns are, what rows are. So I kind of flipped this around just to kind of show that to you. It turns out, and again, I'm going to have to get off this screen when I go to SPSS, but let me go ahead and kind of put the numbers in. We've got 9 people who treated the young person with condescension. And we've got 21 people who didn't treat the young person with condescension. We have 5 people who treated the middle-aged person with condescension, and 25 people who didn't treat the middle-aged person with condescension. And finally, 14 people treated the elderly person with condescension, and 16 people did not treat the elderly person with condescension. So I'm kind of constructing the table from the data this time rather than vice versa. So we could do this by hand. I could calculate expected values for all 6 of these numbers. I don't want to. Already done that tonight and tired of it. Doesn't take me long to get tired of it. You are too. Okay, so I'm going to go back to my SPSS document and notice I've got 3 different ages, 1s, 2s, and 3s. They were either condescending or they were not. Actually, I used 0s and 1s here. I think I used, let's see. Yeah, 0. Okay, 0 is not condescending, 1 is condescending. See, so you can label them however you want to. There's nothing magic about 1 being yes or 2 being no. As long as you know and you enter the right kind of data. Okay, so again, 21 people treated the young person without condescension. 9 people treated the young person with condescension, and so on. So these numbers here are the same ones I put in the body of that table just now. So let's analyze. What do we do first? As he points to data. So we're going to weight cases, and we're going again. This is, as I said before, it's pretty much if you use the word number for the number column, you're always going to do it by number. So I'm going to weight these by number because again, that's the only really quantifiable variable we have. More number represents more of something. Where in condescension, you just 0s and 1s are just yes or no's, just like a toggle switch. It doesn't make any sense to calculate the average condescension with these kind of data. There's my pesky output window, which I don't want. I'm going to go to Analyze, Descriptive Statistics. Remember where? Crosstabs. And this asks me to pick out my rows and columns. In this case, I think I had my rows were condescension and my columns were the age. No, I had it backwards. Never mind. The age was the rows, the condescension was the columns. Is that right? It actually doesn't even matter here. So we're going to go to statistics, and we want the chi-square, and we want the find Kramer V. And I may just walk through a brief review of the write-up here, but again, you're not assigned that. So I like that. We're going to go to cells, and here's the place where we say, hey, go ahead and calculate those expected values while you're at it. So I'm going to go click continue, and I'm going to click 0 and get my output window. And as messy as this is, the two things we mainly want to look at are this 0.0, well, that's the one thing we may not want to look at, the 0.042. That means there does seem to be a difference in condescension according to how old the person is. But now, what I don't know which way. Is there a difference between young and middle, young and old, or middle and old? Kind of like those pairwise comparisons for the ANOVA. It's exactly like that. No, you wouldn't do ANOVA. We're going to have to follow up, but we're going to, since you asked that question, we're going to have to follow up manually. We're going to have to look at the pairs individually. We don't just have a one big, you got to do all the follow-up stuff. We're going to say, and I won't go through all of it, but we're going to say, what is the difference between young and middle? We'll pick something. We'll pick that. Say, but the answer is yes. There's a difference somewhere. So the second part, I told you I'd save it to this example, and here it is. The second part is, okay, let's see where that difference is. I also will say that here's the magic sentence you write. Chi-square 2, what do you think 2 is? Degrees of freedom. But here's something else you also put in there. You have to put the size at the end, because in this case, the degrees of freedom didn't have to do with how many numbers you had. It had to do with how many categories you had. So you've got to give it the value of n. So chi-squared for 2 degrees of freedom and an n equals 90. That value is, well, I said there's something different. It's higher. Well, here it is. There's the other thing. Is equal to 6.325. And the p-value is equal to 0.042. Do you see where the 6.325 and the 0.042 come from? Now, I will tell you, sometimes this is kind of hard to follow in Green and Salcombe because they round it to 2 decimal places. So they're going to call it 6.33 or 6.32. I guess they round down. And then they're going to call the p-value just plain old 0.04. So it's a little hard to recognize sometimes. But here's the sentence like those t-values and f-values and all those other values that we've written as the heart of our write-up. So that's what we write there. And I also mentioned we report this find Kramer V, and they're almost always the same number. Again, it's something you report like effect size in a write-up. If any of you choose to do a chi-square for the write-up, you can use this pattern in the book. I'm not going to do much more than walk through it, and I'll give you, again, some difficulty points if you want to try that. So, what we know now is there is a significant difference somewhere, but I don't know between which 2 groups. So I've got to do a follow-up analysis. And if you'll follow with me, and I'm going to do the steps on the bottom of page. Actually, it's not that far down, is it? Oh, there. Yeah, 371. I was on the wrong page. This is the post hoc, yes. I'm going to go ahead and look. I'll keep the output window because this is going to still pertain to. Well, how do I get to the other one there? I did not do, no, I don't have that option. Okay, let's say that I want to compare young and middle-aged. So I'm going to have to go back to data. Instead of weight cases, I'm going to have to select cases. And we've done this before. At least I've showed you this before. I only want to do the cases where we've got young and middle-aged. I only want the ages 1s and 2s. So I'm going to look at satisfying a condition and clicking the if button. Again, you'll need to rewind this recording a couple times. I want to know what happens if age is equal to 1 or age is equal to 2. Those are the only ones. I want to wipe out all the age of 3s. There are spaces here, yes. I'm 10% sure. We'll find out in just a second. Or age is equal to 2. Not and, it's got to be or. I want all the ones, either they're 1s or they're 2s if I want them. So when I click continue, watch what happens. When I get rid of this, watch what happens. When I go back to find my data set, watch what happens. There it is. It marks out the ones where age is 3. See how it marks those out? So I'm going to do the same analysis, but I'm throwing out the 3s. So I'm going to go to, same thing, analyze, descriptives, crosstabs. Everything else is in place. I don't have to put anything else there. I'm just ready to click OK. So is there a significance between the condescension of young and middle-aged? If I look at my chi-square test, and I want, here's my chi-square table, and I want the Pearson line again, and I get that value, again, that's our p-value, even though it labels it differently, it doesn't even use the SIG. That's not less than 0.05. So there's not a significant difference between young and middle. It must be somewhere else. So I might do a follow-up analysis next time, instead of throwing out the 3s, throwing out the 2s, or throwing out the 1s. Those are the only other 2 we can do. You have to do each one of them by themselves, yeah. And that, again, that's kind of crummy. It just, why doesn't it give you that like it does for an analysis of variance? But it doesn't. Because all I want to look at is that number. Why can't it just give you pairwise asymptotic significance like that? But it doesn't. So that's a brief word about follow-up. And I'm not going to overly dwell on follow-up because your homework's only going to have 2 categories. So if there's a significant difference between the 2 categories. Only if there are 3 or more do you have to do follow-up. It's like if you're doing a t-test between, say, values from men and values from women. You could run that as an analysis of difference, but if you find there's significance, there's only one place it could be, and that's between men and women. So there's a quick view of the follow-up. I concentrated more on the chi-squared itself, the first step, the do you know what time it is kind of step. So I hope that was helpful. And again, the last APA write-up you have to do is your choice. You can do another t-test, you can do another correlation, you can do another ANOVA if you want to, you can do a chi-square if you want to. And some people will probably try that. And I've thought about just requiring chi-square for the 4th, but I hate to not give some choice somewhere. Be brave and do it. Okay. Okay, that is all the new stuff in the course I have to talk about. Thus endeth the new content of 7810. Yes. No. No, that's not it. Anyway, so the homework will be on the WHIT book. It's number, as I say, it's the Titanic question. It's on page 445, exercise 1914. The homework is on page 445 of the WHIT book, 1914. It had to do with, and I learned this, the first time I used this example, I didn't know what steerage meant. I didn't know that. It means you're housed lower in the ship. I didn't. Okay, anyway, I know that now. So the example kind of makes sense. So, what's the relationship between where you were housed and whether you were likely to survive or not? Is there a significant difference in the survival rates between being housed in steerage and being housed in the cabin areas? So there's no, if the answer is there's a significant difference, there's no follow-up to be done. It's just what's the difference between steerage and cabin if there's a difference. So the example is on page, again, bottom page 445. Use SPSS. You'll kind of have to make your rows and columns just like we've done through with a couple examples already this evening. And go from there. Any other questions, thoughts, comments?